Antarctica, a continent of extremes. It's the coldest, windiest, and driest place on Earth, yet nature finds a way to surprise us. The Taylor Glacier flows towards the Ross Sea. From a fissure, a crimson torrent spills out. This is Blood Falls, baffling scientists for over a century. For centuries, the Taylor Glacier held on to its secret. Then, in 1911, a team of explorers led by geologist Griffith Taylor stumbled upon this crimson cascade. Their initial theory, red algae staining the water, proved incorrect. It wasn't until much later that scientists began to unravel the true mystery of Blood Falls. The source of the falls is an ancient subglacial lake, trapped beneath the ice for millions of years. This lake, isolated from the outside world, harbors a unique ecosystem. It is a brine pool, far saltier than seawater and rich in iron. This iron, reacting with oxygen as it reaches the surface, creates the distinctive blood-red color. But the secrets of Blood Falls run deeper than just its appearance. Imagine a time long before Antarctica was a frozen wasteland. Millions of years ago, this continent was a warmer, wetter place, covered in forests and teeming with life. As temperatures plummeted and the ice sheets advanced, seawater became trapped inland, forming isolated lakes beneath the growing glaciers. One such lake, now buried beneath the Taylor Glacier, holds the key to Blood Falls mysteries. This subglacial lake is a time capsule, preserving a snapshot of an ancient ecosystem. Cut off from sunlight and the atmosphere, the lake's waters have evolved in isolation, creating a unique chemical cocktail unlike anything found elsewhere on Earth. And within this alien environment, life has found a way to thrive. The water that feeds Blood Falls is no ordinary water. It's a hypersaline brine, containing several times the salt concentration of seawater. But the real star of the show is iron. This iron, dissolved in the brine, originates from the bedrock beneath the glacier. Over millennia, the weight of the ice has ground the rock into a fine powder, releasing iron into the trapped lake water. This iron-rich brine is the lifeblood of Blood Falls. As it escapes the glacier's grasp and meets the oxygen-rich air, a chemical transformation occurs. The iron, previously dissolved in the water, reacts with oxygen, oxidizing rapidly. This process, similar to how rust forms on metal, is what gives Blood Falls its shocking red hue. The high salt content of the subglacial lake plays a crucial role in Blood Falls' existence. Saltwater has a lower freezing point than freshwater. This, combined with the pressure from the glacier above, prevents the lake from freezing solid, even at sub-zero temperatures. Furthermore, the density difference between the hypersaline brine and the surrounding freshwater ice creates pressure gradients. These gradients force the brine upwards through cracks and fissures in the glacier, eventually finding its way to the surface at Blood Falls. This constant flow ensures a steady supply of iron-rich water, perpetuating the waterfall's crimson spectacle. The Taylor Glacier acts as a massive dam, holding back the immense pressure of the trapped subglacial lake. But this dam isn't perfect. Cracks and fissures, formed by the glacier's movement over the uneven bedrock, provide escape routes for the pressurized brine. These weaknesses in the glacier's armor create a complex subglacial plumbing system. The brine, under pressure from the weight of the ice above, is forced through these channels, seeking the path of least resistance. Blood Falls, therefore, is not a static waterfall but rather a dynamic feature, its flow rate and intensity fluctuating with changes in pressure and the glacier's movements. The transformation of Blood Falls brine from clear to crimson is a dramatic example of nature's artistry, a captivating display of chemistry in action. The key to this alchemy of color lies in the interaction between the iron-rich brine and the oxygen-rich atmosphere, a delicate dance that unfolds as the water meets the air. We're all familiar with oxidation in our daily lives, even if we don't always recognize it. The browning of a sliced apple, the rust forming on a forgotten tool, these are all examples of oxidation at work. In each case, a substance reacts with oxygen, causing a change in its chemical composition and, often, its color. Iron, in its ferrous form, Fe2+, is highly susceptible to oxidation. It transforms into ferric form, Fe3+, forming rust. Rust color varies based on iron oxide type and environmental factors. Bloodfall's red hue is due to high iron content and acidic brine. The transformation occurring at Bloodfalls is not limited to the visible spectrum. While our eyes perceive the dramatic shift from clear to crimson, a much more complex chemical reaction is taking place at the molecular level. Scientists, using sophisticated analytical techniques, have been able to identify the specific iron oxide minerals present in the brine and track their formation over time. These studies reveal that the oxidation of iron in the Bloodfalls brine is not a single-step process, but rather a multi-stage reaction involving a series of intermediate compounds. Each stage is characterized by the formation of different iron oxide minerals, each with its own unique chemical properties and color contributions. The chemical composition of the Bloodfalls brine and the specific iron oxide minerals present provide valuable clues about the subglacial environment from which it originates. By analyzing the ratios of different isotopes within these minerals, scientists can estimate the age of the subglacial lake and the conditions under which it formed. Furthermore, the study of the oxidation process at Bloodfalls has implications beyond Antarctica. Similar iron-rich brines have been found in other extreme environments on Earth, such as deep-sea hydrothermal vents and acidic mine drainage. Understanding how these systems function can provide insights into the limits of life on our planet and potentially guide the search for life beyond Earth. The crimson cascade of Bloodfalls might seem like a scene from a science fiction movie, a desolate landscape devoid of life. But appearances can be deceiving. Hidden within this extreme environment, beneath the ice and within the iron-rich brine, thrives a community of microorganisms uniquely adapted to survive where few others can. These microscopic marvels belong to a category known as extremophiles, organisms that thrive in conditions considered hostile or even lethal to most life forms. The subglacial lake feeding Bloodfalls presents a formidable array of challenges: permanent darkness, frigid temperatures, high salinity, and a lack of oxygen. Yet, life persists. The extremophiles of Bloodfalls are not recent arrivals. They are descendants of ancient microbial communities that inhabited the surface waters millions of years ago, before Antarctica froze over. As the ice sheets advanced, these microorganisms were trapped beneath the glacier, isolated from the outside world. Cut off from sunlight, the primary source of energy for most ecosystems, these trapped communities had to find alternative ways to survive. Over millennia, they evolved the ability to extract energy from the chemical imbalances within their environment, a process known as chemosynthesis. The chemosynthetic lifestyle of Bloodfalls extremophiles is a testament to life's remarkable adaptability. Instead of relying on sunlight to convert carbon dioxide into organic matter, these microorganisms utilize energy released from chemical reactions involving iron and sulfur compounds present in the brine. This unique metabolism allows them to thrive in the absence of light, extracting energy from the chemical imbalances within the subglacial lake. They have also evolved adaptations to cope with the high salinity and frigid temperatures, their cellular machinery fine-tuned to function under these extreme conditions. The discovery of life in Bloodfalls has profound implications for astrobiology. It expands our understanding of life's limits and potential in extreme environments. Icy moons like Europa seem more promising for life. Bloodfalls fuels our search for life beyond Earth. The discovery of life thriving in the extreme environment of Bloodfalls has ignited our imagination, offering a tantalizing glimpse into the potential for life beyond Earth. Here, in this frigid corner of Antarctica, we find an ecosystem that challenges our preconceived notions of habitability, hinting at the possibility of life existing in places we once thought impossible. Astrobiologists, scientists who study the origins, evolution, and distribution of life in the universe, view Bloodfalls as a valuable analog environment. By studying the extremophiles that thrive in this challenging habitat, we gain insights into the potential for life to exist in other extreme environments throughout our solar system and beyond. The presence of iron in the Bloodfalls ecosystem, a key factor in its unique characteristics, resonates with our understanding of other celestial bodies. Mars, often dubbed the Red Planet, owes its distinctive hue to the presence of iron oxide, the same compound responsible for the crimson cascade of Bloodfalls. This iron connection is more than just a visual similarity. It hints at the possibility that similar geochemical processes, driven by the interaction of iron, water, and microorganisms, might have occurred on Mars in its distant past, potentially supporting microbial life forms. Our search for extraterrestrial life extends beyond Mars. The icy moons of Jupiter and Saturn, particularly Europa and Enceladus, harbor vast subsurface oceans that astrobiologists believe could hold potential for life. These oceans, shielded from the harsh radiation of space by thick layers of ice, are thought to be rich in salts and minerals, similar to the subglacial lake-feeding Bloodfalls. Furthermore, there is evidence to suggest that these moons might have hydrothermal activity on their ocean floors, similar to the hydrothermal vents found in Earth's deep oceans. These vents, spewing hot, chemically rich water into the surrounding environment, could provide the energy sources necessary to support chemosynthetic life forms much like those found in Bloodfalls. The study of extremophiles in environments like Bloodfalls provides a framework for understanding potential life in the universe. Life on other planets might be vastly different, but the building blocks and chemical processes are likely universal. Life's resilience fuels our optimism in the search for extraterrestrial life. Bloodfalls reminds us that life finds a way, even in the most unexpected places. Bloodfalls is not a static phenomenon. It pulsates with the rhythms of the Antarctic seasons. This dynamic nature adds complexity to this natural wonder. During the harsh winter, temperatures plummet, and the McMurdo dry valleys are plunged into darkness. The flow slows to a trickle, often freezing at the surface. The falls, however, never truly cease. As we marvel at the wonders of Bloodfalls, we must also acknowledge the looming threat of climate change. Antarctica, the coldest continent on Earth, is experiencing some of the most dramatic effects of a warming planet, and these changes have the potential to alter the delicate balance that sustains this unique ecosystem. Rising temperatures could lead to increased melting of glaciers, including the Taylor Glacier, potentially disrupting the pressure gradients that drive the flow of brine to Bloodfalls. Changes in the frequency and intensity of snowfall could also impact the subglacial lake, altering its salinity and chemical composition. These shifts could have cascading effects on the extremophile communities that call Bloodfalls home, potentially threatening their survival. Sentinels of change. Bloodfalls, with its sensitivity to environmental changes, serves as a sentinel, a warning beacon highlighting the interconnectedness of our planet's systems. Scientists are closely monitoring the falls, tracking changes in its flow rate, chemical composition, and microbial life as indicators of broader climate trends. By studying how Bloodfalls responds to these changes, we gain a better understanding of the potential impacts of climate change on other icy environments, both in Antarctica and around the world. This knowledge is crucial for informing conservation efforts, mitigating future risks, and ensuring the preservation of these unique and valuable ecosystems for generations to come. A call for stewardship. Bloodfalls, with its crimson cascade and resilient life forms, stands as a testament to nature's power and fragility. It is a place of extremes where life thrives against all odds, yet vulnerable to climate change. We must protect it. By addressing climate change and promoting sustainability, we ensure it inspires future generations. Bloodfalls, a crimson stain on a pristine white canvas, stands as a powerful symbol of nature's enduring capacity for wonder. It is a portal to hidden worlds beneath the ice. It challenges our assumptions about life's limits. The discovery of thriving microbial communities has revolutionized our understanding. It fuels our imagination about life on other planets. The Crimson Legacy. The crimson legacy of Bloodfalls extends beyond science. It reminds us of the interconnectedness of our planet's systems and the impact of climate change. Changes in Bloodfalls serve as a barometer for the health of the Antarctic ecosystem. We are reminded of our responsibility to protect this fragile planet and its biodiversity.